Hello folks, and welcome back to Skybound on the Ground with Michael Lombard. I'll be filling in for Michael Lombard today. We are on the second half of the chapter on flight instruments. We learned about the three instruments last time that can tell us how fast we're going, how high we are, and how fast we're changing how high we are. And today I promised I would tell you about one of the instruments that I personally think is the coolest instrument that we have in the airplane. In fact, it is so cool, it can actually tell you what your attitude is. If you have a good attitude or a bad attitude. Wow, that sounds like an amazing instrument. Well, how in the world is that possible? Let us find out. The first thing that we have to understand is something to do with gyroscopes. Now, believe it or not, you have actually done quite a lot of work with gyroscopes without actually knowing it. Your bicycle has two gyroscopes on it. That's right, it has a front wheel and a back wheel. A gyroscope is basically a spinning disc. I couldn't fit a bicycle wheel in the frame here, so I brought my paper plate again from when we were talking about aircraft propellers and how they basically work as gyroscopes as well. And so, let me try to get this straightened out here. So when you spin a disc, it becomes a gyroscope, and it has certain properties. There's two properties, and I don't know if you've ever tried this, but perhaps in your high school physics class, you were able to grab one of these bicycle wheels like this, hold it by the, whatever you call it, like an axle or something, and had your friend spin it up, and the first thing you notice is that, oh wow, as you spin it up, it becomes rigid. You can't really twist it, and that's exactly why you're able to stay on your bicycle without falling off, and without having to use training wheels, of course. So, rigidity in space is that first principle. When you get a disc spinning, it gets this this property where it won't fall over. It's just going to stay in the same plane where you got it spinning. So rigidity in space, that's the first property. The second property is a little bit more weird. Maybe perhaps when you were spinning your bicycle wheel, you discovered that if you tried to twist it, or sorry, if you tried to torque it, like to lean it over on its side, it did something weird. So let's say we tried to twist it like this. Well, what would happen is it would actually go like that. And that's because, or sorry, it would actually go like this. And that's because of this principle called precession. I don't know if you learned that in your high school physics class, but that's exactly what it is. Gyroscopic precession. When you put in a force into a spinning disc, it's going to come out again, but this time as it goes in, it makes a 90-degree turn in the direction that the disc is spinning, and it comes out in that new direction. So this is what it looks like. Let's say we have, so we're going to try to torque it over like that, and so we have our force right here pointing upwards. There's our three-dimensional arrow, and so we push it in. That force goes in, turns 90 degrees in the direction that the wheel is spinning, and comes out in that new direction. So that's what it's, let me try to draw a nice three-dimensional arrow. So this is what it's going to, okay. Okay. And then just do the erasing, and you can see what I'm talking about. So what we have tried to do, let me turn this around so you can see it. What we've tried to do is try to twist it like this, and what ends up happening is it starts rotating this direction, and that is gyroscopic precession. These two principles of a gyroscope make it very useful. We can actually harness these two principles to make some very useful instruments for our flight deck. And I'm sure you're already thinking of one application for rigidity in space, but we're going to save that one for a little bit later, because we're going to deal first with gyroscopic precession. How in the world can we use that for an instrument? Well, let's you and I build an instrument. So let's get a instrument case going here. So here is our instrument case, and there's the front of the instrument, there's the back of the instrument, and let's put a gyroscope in here. And what we're going to do is we're going to mount this gyroscope vertically, kind of like a bicycle wheel, and we're also going to hold it with something that looks like a kind of like a bicycle wheel fork. So that is how we're going to hold it in place. And that's going to be connected to the backside of the face of the instrument. Okay, so now we spin this deal here. And what happens, and oh, hold on, let me just check my book here to make sure I got the direction of motion correctly. And okay, it's supposed to be actually rotating the other way. So we are doing things on the fly because we are pilots, guys. Or we're going to be pilots. So, okay, so now we're going to spin up our gyro right there. And what's going to happen is it's mounted in this vertical plane here, and we have like the bicycle fork holding it right there. And so we spin it up, and now if we turn the airplane, let's say we turn the airplane, that means that the airplane is going to be yawing. So if you yaw the airplane, you're going to be exerting a force onto that gyro. It's going to be kind of like you're going to be trying to twist it. And if you try to twist it, that means it's going to lean over. And we can use that to tell if we are turning the airplane or not. And if we want to find out how fast our airplane is turning, all we have to do is figure out, or look and see how much that gyro is leaning over. So using that principle of precession, we have ourselves a turn indicator. So let's take a look at what the instrument face looks like, how they've set it up. So you'll have a needle like so. Let's make it a little bit shorter. So that's the hinge. So the needle swings back and forth, and when the needle is pointing straight up, that means you are not turning. But as the airplane yaws around, then that means the the gyro, is getting this force placed on it, and so it's going to deflect off to one side or the other depending on which way you're turning, and so this needle is going to get deflected to the side. These when you're up at the top, of course that's 0. When you deflect to one of these little marks here, when the needle gets all the way to one side or the other, then you are in a standard rate turn, meaning that it'll take you exactly 2 minutes to make a 360-degree turn, or 3 degrees per second. So that's our turn coordinator. Now, if we just put a little extra something on the face of this instrument, we put something called an inclinometer. An inclinometer, don't worry about the gyros or anything. This is just a hollow tube that's put on the face of the instrument, and it has a ball in it. Such a simple thing and such a big name for it, an inclinometer. Just a hollow tube with a ball. Well, what this does is it helps us keep our turns coordinated, and this goes back to that experiment that I was trying to do on board the airliners when I wanted to see if I could figure out if the plane was in a bank by dangling an object on a string, like a pencil or a pen like this. And it never seemed to work because it was always hanging straight down, and the reason why was because the airplane was in coordinated flight. You had the force was straight down through the floor of the airplane instead of just having gravity alone working, where that would pull the object off to the side. So this ball is the exact same thing as the pencil hanging on the string, and this helps us tell if we are in coordinated flight. What happens if you bank the airplane and we get the airplane into, let's say, put the airplane in a left-hand turn, and we're not using enough rudder, and so the airplane is actually slipping into the turn. And so, you know, the airplane is it is banked and it is turning, but the rate of turn isn't enough, and we're actually slipping. You'll actually feel yourself kind of slipping off to towards the side that the airplane's banking. And what do you know? That ball's going to be off to that side as well. And so that is during a slip. And then what the other case is say we are also turning the airplane left, but we don't have enough bank for the rate of turn that we're using, and perhaps we're stepping on the rudder too much. And so you can actually feel as if when you're going around the corner of the car, your friend turns the wheel really hard and you get flung to the other side. So you're going to be squished up against the opposite side of the direction you're turning. That ball is going to be off to the other side, and so that's in a skidding turn. So how do we keep that ball in the center? A really easy way to remember it so that you can keep your mind straight as to what you're supposed to do with the rudder is to step on the ball. You have two rudder pedals. If the ball's on the left, you just step on the left pedal and that puts it back in the middle. If the ball's on the right, you just step more on the right pedal and that'll put the ball back in the middle. So that's the inclinometer. And because you put the inclinometer in this turn indicator, we call this together, we call it the turn and slip. Turn and slip indicator. I don't know why they don't say turn and slip and skid indicator. That would be a little bit wordy. Now they came up with a refinement to the inside of the instrument, because they realized that, well, this only tells us if we're turning. It doesn't tell us any type of bank information. So the airplane could be flying in a bank, maybe knife edge or something like that, and not actually turning, but just flying along in a bank. And so it doesn't give you any roll or any type of information like that. It just tells you if you're turning and how fast. So what they did a very simple modification of the instrument. And so instead of having that little bicycle fork straight out like that, they tilted it downwards. And so now the instrument, now the gyro would sense if the airplane is rolling as well as when it's yawing. And so as you're rolling the plane into the turn, then you would get a indication on the dial showing that initial roll rate. And then once you actually got established in the turn, then it would show you your rate of turn. And so they gave it a new name for the instrument, and it also looks a little bit different. They put a little miniature airplane in here, and we call this now the turn coordinator. And so you would have little markings on the side now, and so you just look at where your wings are, if the airplane banks or whatnot, and you could tell how initially it would show you your rate of roll, and then it shows you your rate of turn. So that's just the rate of turn, and turn coordinators. The turn coordinator is kind of the old school way, and this is what you'll probably see in the airplanes that you fly. So we have learned how to apply the principle of precession, and now let's get to that principle of rigidity of space and how we can use that. And I wonder if you're thinking what I'm thinking, and that is, what if we hooked it up? So let's make ourselves another instrument here, and let me improve my drawing while I'm at it. So, okay, so here's our instrument, and there's the instrument face there. And here's the back once again. And so we're going to put ourselves a little gyro in here once again. This time we're going to have it oriented like in a horizontal plane. Kind of like the horizon. Ooh, this is cool. So, and what we're going to do, instead of hooking it up with like a bicycle fork or whatever, we're going to have it actually have a little bit more freedom of to be able to move. While this isn't going to move, the instrument case is actually going to move around it. So we're going to hook it up with some, we call these gimbals, so they're basically just rings that it's attached inside. And so a ring that way and a ring that way, and then we just have these rings attached to the back. And then, so what happens now is this is spinning, and because of rigidity in space, it's going to stay in the exact same position relative to wherever you set it in the first place. In this case, it's going to be level with the horizon. So it's going to stay in that exact same position as everything else turns around it. Isn't that what we're supposed to be like? You know, in our spiritual walks, we're supposed to be grounded, and even if the world is turning all around us and falling apart, we're still supposed to remain level, and that's because we have a source of strength. Anyway, so that's just a little spiritual application there. I need to think a little bit more about how I could tie in some of these things. That just popped into my mind. But anyway, so this is going to stay in the exact same position relative to the horizon, and so the airplane will be pitching The airplane can be pitching, rolling, turning, whatever, and that's just going to stay right there no matter what the airplane is doing. And so we can hook that up. All we have to do is hook that up to the instrument face over here. And so we have something that we do that with. And we now have a little miniature horizon inside our cockpit. And this is what it looks like. We'll have a little miniature airplane represented there. Little dot there. I think that's like a pilot or something. I don't know. And we will have the horizon. And then, so that horizon is hooked up to the gyro. And so as the airplane banks or pitches, you will see a corresponding change on the instrument. And that horizon will always be going where the real horizon is. It should look exactly like what's happening outside the window. So let's say we put the airplane into a bank. So here's our little miniature airplane. Actually, I'm just going to do it a little bit simpler so that I don't spend half the time drawing. And so we put the airplane, let's say we put the airplane into a right-hand bank. We roll the airplane, and so the horizon's like this, and our gyro's like that. And so this is what it's going to look like on the instrument. And you'll be able to see what your bank angle is and stuff like that. And then what happens if we put the airplane into a climb or a descent? Let's put it into a climb, and this is what it'll look like. So the horizon is going to be way down there. We're putting it into a really steep climb. Oh yeah, there's usually tick marks to show you degrees of how much pitch you're using. So yeah, so we have the airplane in a climb right there. So this is why I think it's the coolest instrument, because it is basically a little miniature horizon in your cockpit. And they actually used to call it the artificial horizon. They have a more modern name for it now. It's called the attitude indicator. And this is where we find out our attitude, if it's a good attitude or a bad attitude. Because attitude, when you're talking aviation, is your relationship to the horizon. So if you have a good attitude, you're not going to be in any kind of crazy position. If you have a bad attitude, well, you're going to want to get out of that attitude, and you can tell by looking at your instrument, your attitude indicator. And this is why it's such an important instrument to have in your plane if you happen to find yourself inadvertently entering the clouds, because suddenly you can't see the horizon anymore. You need to have some reference. And so you now have that reference on board. Learn how to use that. You actually get emergency training while you're doing your private pilot's license, and when you go into your instrument rating, you learn how to fly this. You'll just be an old hat at that by the time you're done with your instrument rating. And so, yeah, if you ever find yourself inadvertently in the clouds, rely on this and turn around, because you probably were out of the clouds a few minutes ago, and so you could get yourself back out by doing a 180. So, this is cool, but there is one other cool thing that we can do with a gyro. We have 3 instruments that are gyroscopically actuated or powered, so let's make one more instrument. So let's get our instrument case here again. There's the face of the instrument and the back. And we're going to get our gyro, we're going to get a gyro, and we're going to mount this gyro vertically again. Alright. This is kind of starting to look a little bit like the turn coordinator that we did at the beginning. But there's a difference, because we are going to have this in a set of gimbals just like we did with the attitude indicator. And so this is going to be freely, the instrument is going to be able to move around it just like the attitude indicator was set up, but this is mounted in a different plane. It's mounted in the vertical plane. And guess where we're going to point that when we get it all set up in the beginning? We're going to point it at north. That is a great idea, isn't it? So we have our gyro. It's pointing at north, and so we got a couple gimbals here. And so Okay, so it's hooked up here, and this goes all the way to the instrument face. So now, as the airplane is turning and rolling and whatnot, this is always going to be pointing at north, pointing at magnetic north or whatever north you happen to set in there. And so it doesn't matter if the airplane's bouncing around, we are going to be able to see which way we are actually heading. And so let's look at the face of the instrument. We're going to turn this into a heading indicator. So we'll have a little representation of our airplane there. And then we have the directions of the compass on there. I'll show you a little bit later on how to read this. But here is our turn indicator. And it's basically like a stabilized compass. Because you'll get to realize that as you're trying to fly a plane, if you try to turn the airplane and follow the compass as it turns, you're going to run into all sorts of problems. First of all, the compass bounces like crazy. If there's any turbulence, it's going to wiggle all over the place, and then you get turning errors and acceleration errors and all sorts of weird stuff with compasses. They're only accurate when you're flying straight and level. So that's not very helpful for making turns. So it's really nice to have a gyroscopically stabilized turn indicator that is just going to turn. That's just going to indicate what your heading is, even if you're in turbulence, and it's always going to be there for you. So that is your turn. That's your turn indicator, and these are these all rely on the principle. This one relies on the principle of rigidity in space, and we learned about precession and how we could harness that. But in this case, precession actually can get in the way. Because it will actually cause this to drift off of where it was before. The reason precession actually happens is because, well, first of all, you're going to have a little bit of friction going on from the bearings. There's no way to have something without any friction. And so depending on how old the instrument is and how worn out stuff is, there's going to be friction going on. So it's going to drift. It's because that friction introduces a little bit of force, and so that makes the gyro precess in a direction that is off from where it's supposed to be pointing. Even if you had no drift from no drift from dirt and your bearings getting worn up and stuff. Man, I'm really getting tongue-tied here. Friction! That was the word I was looking for. Even if you had no drift because of friction, you still have the Earth rotating. And if this were remaining in the exact same position, and the Earth rotates under you, that means this is now off. And the Earth rotates at 15 degrees per hour. So that means in an hour, you would be 15 degrees off. So you just make it a habit of every 15 to 20 minutes, you always realign your heading indicator with your magnetic compass. You have a little knob that you can do that with. So that's a nice thing that you can do. Realign your heading indicator. I failed to mention that with the attitude indicator, it has certain limits unless you have one that's specifically designed for aerobatics. You can actually tumble your attitude indicator if you get into some sort of an extreme attitude. It's just going to throw it completely out of alignment, and so when you're actually flying straight and level, it's going to give you inaccurate readings. You're going to have to reset that as well. Another thing that can cause your heading indicator to not indicate correctly, as well as your attitude indicator, is if your gyro isn't spinning fast enough. Well, how in the world do your gyros spin in the first place? And this is where we talk about the vacuum system. It's really simple. All you have to do is get air rushing over it, and we put these little vanes in there, and it works kind of like a water wheel on those old sawmills. And so as the air is rushing over it, then it just spins it up. And so we have our gyro instruments hooked up to a vacuum system. We'll have an engine-driven pump over here, and that sucks air from something that's from an outside source. It'll so outside air. It'll pass through some sort of a filter, get filtered, and then it'll just go to the instruments. It'll spin up the gyros as it passes through, and then it goes out. And so this pump over here is just sucking the air, and then it pumps it straight out to the outside again. You'll have some sort of a relief valve that makes sure that you don't get too much pressure inside the system. And then you'll also have a gauge over here that can tell you what your pressure is. Usually it's going to be between 4.5 and 5.5 inches of mercury of pressure inside your vacuum system. And it's important to keep tabs on that while you're in flight, because if your pressure starts getting low, that means your gyros aren't going to be spinning up as fast as they should, and they're going to fall over. Just like when you ride your bicycle too slowly, you end up falling over. I guess the reason why it's a vacuum system and they don't just pump air through here is because if the pump failed and you had pieces coming apart and getting sent out through here, that would ruin the gyros. So they do it the other way around to suck air through. So that's the vacuum system. And now let's talk a little bit about our magnetic compass. I told you how the magnetic compass is quite a bear to work with when you're trying to do turns, and let's see why. First of all, let's learn how to read a compass. This is pretty fun. Remember north. That's going to be that circle has 360 degrees. So we're going to start at 0, and we're going to go all the way around. So east is going to be 90 degrees. South is going to be 180 degrees. West is going to be, I should have put that inside. West is going to be 270 degrees, and then all the way back up to 360, or you start at 0 again. So that's how you read your compass, and the compass itself is going to have these numbers, except with the 0 chopped off of it. So you'll see it written, you'll probably have a north, and then you'll see it written as 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33. And so the way to read this is just put a 0 on it, so that would be 30 degrees. This would be 180 degrees. So that's just how you see the numbers written on the compass dial. Now, how does a compass work? You know about this from your Boy Scouts days or elementary school or whatever. You have a needle, and that points towards north. It's fair and simple. Well, we have a compass in the cockpit, and we're looking at this from the top. We don't have our compass sitting in our laps and we're looking down at the compass while we're flying the airplane. Now, we have it mounted up possibly on top of the aircraft, on top of the instrument panel on the dash right there. So maybe here's your panel over here. You're going to have the compass up there. And because you have the compass like that, they actually put the numbers on the side of the compass. So when you look at the compass, you're going to see the window right there. And so you're going to see, okay, the compass is pointing at north. They have to put that on the back side of the compass just because you're looking at the back side of it, because you're looking at the side. So it's pointing at north. You're actually looking at this end right there. It just makes it a little bit confusing. You just have to realize that it's set up like that, because otherwise you'll get confused when you see that the numbers seem to go the wrong direction, because you think, oh, we turn to the right so that we can start going towards the east, but that looks like it's on the left side. And then also when you actually turn the airplane, then this turns and looks like it's turning the opposite direction. Well, this is actually staying still and you're turning. So just realize that. That's how the compass is set up. And there are some quirks to our compass that I was mentioning. Well, first of all, there is the quirk that the compass always points to magnetic north. Well, isn't that what compasses are supposed to do? Yes, they are. But when you have magnetic north at a different place than the real North Pole, that creates a problem. If you look at our Earth, you will realize that at the place where the Earth rotates, this is the geographic North Pole. let's say, okay, so there's North America and Greenland over there and whatnot. Terrible map, I know. So that's the geographic North Pole. That's where the Earth rotates around. While the magnetic North Pole is actually several hundred miles away, and it's always moving. It's drifting by, I don't know, there's a certain rate that it drifts by. So it was recently over in the very upper parts of Canada, and now it's moved a little bit off into the Arctic Ocean. So your compass is always going to be pointing at that instead of the real North Pole. And if you're doing your maps are always going to be oriented in relation to the real North Pole, because this other thing is changing all the time. So that constitutes a problem. Say we want to go north, and we want to fly north, so normally we would fly a heading of 360 degrees or 000, whatever you want to call it. But our compass, if we're over here in California, there's actually a 15-degree difference between magnetic north and what we call true north. So if you follow magnetic north on your compass, you're going to end up quite a ways away from your destination of where you're wanting to go, because there's a 15-degree difference. So what you have to do is you actually have to fly a heading of 345 degrees, and we're going to learn how we can figure this out, how to calculate that out when we get to cross-country planning in our upcoming lessons. So that's called magnetic variation, the variation between true north and magnetic north. So that's something you have to keep in mind when you're navigating around. The other thing another quirk that the compass has is called magnetic deviation. And that's because when you have radios and electronics on in your cockpit, they create their own little magnetic fields, and the compass is going to want to deviate just a little bit to point at that. And so what airplane maintenance technicians do is they adjust for that, but there might still be a little bit of deviation error that they can't rule out. So they'll give you a little card, and they'll put that on the bottom of the compass with heading corrections. And so if you're wanting to fly 270 degrees, they'll say, okay, you need to steer 273. And that's just because of the little magnetic fields that are in your cockpit causing your compass to deviate just a little bit. All right, so that's some of the quirks. We have one more quirk, or two more quirks, that are kind of related, and that's because of magnetic dip, compass dip errors. If you look at the lines of magnetism, when you have basically what happens, you have lines of magnetism. That's what the compass needle aligns itself with so that it points to the North Pole. Well, these lines of magnetism dip down into the Earth when you get to the poles. And when you're over the equator, they're actually completely parallel with the Earth's surface, and then as you get closer to the North Pole, then they start dipping down. While the other feature of the magnetic compass is that it's going to, in addition to wanting to align itself with these lines so that it's pointing towards the pole, it's also going to want to be parallel to them. So if you're over the equator, that means the needle is going to be parallel to the ground, but as you get closer to the north, as you get further and further north, that needle is want to point downwards towards the center of that North Pole right there. And it wants to align itself with these lines of magnetism. Well, that gives you some problems when you're flying along with your compass. First of all, if you're flying along straight and level, that's no problem. Straight and level flight, your compass is going to be as accurate as it's ever going to get. And but when you fly, when you start putting your airplane into a turn, that's when you're going to have some interesting things happen. So here's the compass in straight and level, and let's just try to put some perspective there. It's pointing at the North Pole. So you're flying on a north heading, and we're going to have, this is what we're going to see on the compass card, because we're looking at the back on the side of it. And so that's what we're going to see. And now we put the airplane into a bank. Okay, so what's supposed to happen is this is supposed to keep pointing north. But what happens is that now that you've put it in a bank, that needle can actually start pointing a little bit down towards into the ground. And so it's going to point itself a little bit off. And so whereas the so we've rolled the airplane, and so now it's indicating, even though you've rolled the airplane into a right-hand turn, that needle is dipping down, and so it's going to make it look as if you're turning in the opposite direction. We should be heading towards 030 degrees, but this thing's dipping down, so it's actually moving towards 330 degrees. It'll end up turning in the right direction as you continue your turn, but it's going to lag behind you when you're turning from a north heading. Let's say you're on a south heading. And so this is going to be showing south, and off to the side it'll be, so the needle's pointing like this, because the north is this way. Okay, and let me just get right here. Okay, so now we're going to roll the airplane into a right-hand turn again, and let's see what happens. Ooh, so the airplane's in a bank, and now this needle has an opportunity to dip itself down again and try to align itself with those lines of magnetism which are dipping into the earth. And so it's going to cant itself off to the side, turn a little bit too much. And so what happens now is the indication we are doing a turn to the right, yeah, okay. I just get confused myself as well. So now it makes it look, so we're heading towards 210 degrees, but we're not there yet. We just started our turn, but it is actually anticipating our turn. It's going faster. It's leading our turn. And so when you're on a southerly heading and you roll the airplane into a bank, make this tendency of the needle to want to dip down towards this pole is going to make the compass indicate a turn in the direction you're going, but it's going to indicate at a faster rate. It's going to jump the gun, per se. So that is dip error. And what they do to kind of compensate for this is they put little weights on the south end of the needle so that it kind of weights it down and it keeps it from pointing all the way down, so it'll kind of compensate for that. So if you have that needle, if you have that weight there, then that'll make it not so much of a factor. It'll still happen. But putting those weights actually introduces another little problem now. And that's when we are accelerating or decelerating on a east or west heading. So first of all, to remember what we just talked about, there's a little mnemonic, and it's called NO, north opposite. If you're on a northerly heading, just remember that when you start a turn, the compass is going to momentarily indicate a turn in the opposite direction, and then when it starts catching up to you, it's going to be lagging behind you until you get to east or west. And then you remember north opposite. When you're on the south, it's just going to overshoot. It's going to jump the gun. All right, so now we are on a heading east. We're on an east heading, and so this is what our compass looks like. And let me just get the numbers right. Okay, so that's what it's going to be like, and then more headings over there. Compass is going to be pointing like this. That's where north is. And we're not going to do a turn because it's not going to make much of a difference. But if we accelerate, now having that little weight on the end that was supposed to compensate for dip error, that's going to throw a little curveball into the mix. As you accelerate, that is going to, this has a little bit more mass to it. It's going to resist that acceleration. And so that's going to have the effect of swinging the needle just a little bit that way. So that means that on an when you're accelerating, it's going to point, you're going to have your compass momentarily indicate a turn towards the north. And the opposite is true is if you decelerate. So what happens? That little weight, it's got more mass on the other side, and so as you decelerate, that's going to want to continue going, and so that'll have the effect of swinging the needle this way. And so even though it's supposed to be pointing at magnetic north, it momentarily deviates from that, and it will be pointing more this way. And so when you are decelerating on an easterly or a westerly heading, that means your compass is going to momentarily indicate a turn towards the south. And that is because of those weights that they put on there to try to fix things out. So, folks, we have learned a lot about compasses, and it takes a little bit of reviewing to try to get your mind wrapped around this concept. But just remember that compasses can be quite a bear to deal with. So be thankful for your heading indicator. And what you'll also notice is that the compasses will sometimes get into this oscillation where they're just swinging back and forth between a bunch of headings. You just have to take the average of it, just see, okay, it swings back and forth, and it looks like it's right about the middle is 90 degrees or whatever. So that's a result of all those things put together. That's what might happen. So be thankful for your gyroscopic instruments. And guess what, folks? You and I now have a six-pack from learning all this stuff. A six-pack? What? That's because we have learned the 6 basic instruments that you're going to find on pretty much any airplane panel. We've learned about our airspeed indicator, how fast we're going. We've learned about our attitude indicator, what our attitude is in relation to the horizon and whether it's a good attitude or a bad attitude. Our altimeter, how high we are. We've learned about our rate of climb, our vertical speed indicator, and that shows us how fast we're changing how high we are. And we've learned about our heading indicator, and finally our turn coordinator over here. And these are the 6 basic instruments that will help you out anytime you find yourself in a pickle. Rely on these if you can't see outside, if it's a dark night, if you happen to find yourself in the clouds accidentally, just make sure you don't go back in. You just try to get out of those clouds and use your instruments. These help enhance your flying experience even when it's gray outside. So, now some of these instruments are actually required to be on your airplane and they're required to be operative. How do we tell the difference between well, what if one of them is broken when we come to the airport? How do we know which instruments we are allowed to fly with if they're broken, and which ones we cannot absolutely fly with unless they are operating? So we're going to learn about that in the next lesson, so stay tuned for more Skybound on the Ground. I was just going to tell you a helpful mnemonic for remembering which way your compass is going to turn when you accelerate and decelerate on a easterly or westerly heading is ANDS. That's for accelerate north, decelerate south. ANDS. See you next time.